In this lecture, we're going to learn about concepts. Again, concepts are a mechanism we have in place in C++20 to place constraints on our function templates. For example, we can use concepts to specify that we want our function template to only be called with integers or doubles or strings or whatever, and when somebody violates our concept, they're going to get a compiler error. In this lecture, I am going to show you how you can set up your concept and different syntaxes you can use and how we can understand them. But before we do that, please note that there are two sides to concepts. There are concepts that are standard and built into the C++ standard library. And those are ready to use, and these are what we're going to be using in this lecture. But know that you can also build your own concepts and use them to do whatever it is you want to do. Here are a few examples of built-in concepts we can use from the C++ standard library. We have, for example, a concept we can use to enforce that people call our functions only with integral types. If they violate this, they're going to get a compiler error. We can also enforce for our template parameters to be floating point. We can do all kinds of crazy things. Okay, now that you know this, let's see how we can set up a concept on our function templates. And this is the first syntax we're going to look at. All you really have to do is to put in your template declaration like we have been doing all along. You also have to add in the requires keyword here. After the requires keyword, you're going to specify your concept and specify your template parameter in angle brackets here. When you have this thing in front of your function template like we have here, the function template can only work right if the concept in here is satisfied. And this concept in this case is going to be satisfied if somebody tries to call this function template only with integral types. If they violate that, again, they are going to get a compiler error. Okay, once we have this concept set up, we can look at a piece of code that tries to use it and try to guess what is going to happen. Here is a piece of code we would set up in the main function and try to call our function template. We have two variables of car type. We know that car is an integral type. So if we issue a call like this call is going to work. The template instance is going to be generated and it's going to be called and give us the results that we can print here. This is right. On the second piece of code here, we have two variables of type int. We're going to call them. We're going to call our function template with int. And this is also an integral type. Int is an integral type, so this is going to generate our function template instance, and we're going to call it and get the results that we print here. And if we try to call our function template with double types, the concept is not going to be satisfied and we're going to get some kind of error and our function template instance is not going to be generated. This is really how you can use concepts to force some rules on users of your function templates, if I can say it like that. We have been able to do something like this using type traits and static asserts in the last chapter, but concepts are much cleaner in that they are kind of built into the signature of your function. You don't have to go in the body of your function and set up static asserts. The function is already supporting concepts when you declare and define it, and this is really cool. Okay, this is our first syntax we can use to set up concepts for our function templates, using the requires clause after our template declaration and following that with whatever concept we want to enforce on our function template here. Please note that you can also use type traits directly in the requires clause here, and this is going to work. And this really says that all you really have to put after the requires clause is an expression that can be evaluated at compile time but also results in a Boolean value. Once you satisfy these few requirements, you can really set up your concept however you want. You just have to be careful that the expression can be evaluated at compile time and that it evaluates to a Boolean value. And when the expression evaluates to true, the concept is going to succeed. If the expression evaluates to false, you're going to get a compiler error because the concept is not satisfied. This is how these things work. Now that we have seen the first syntax, I think it is big time we looked at the second way you can set up concepts, and that's going to be in your template declaration. You're going to say template, put in your angle brackets, and inside, instead of saying type name T like we have been doing all along, you just specify your concept directly and say the template parameter like this. Once you do this, this concept is going to be enforced on this function template here. This is just another syntax to really do the same thing. We also have a third syntax we can use if we use auto to set up our function templates. And the way this works is to just add your concept in front of the auto keyword. And once you do this, the compiler is going to enforce for the first parameter and the second parameter to this function to satisfy the integral concepts. So if you have to use auto to set up function templates, this is how you can use concepts to constrain ways in which people use your function. We still have another way we can use concepts in C++, and this is how you do it. You specify your template declaration like we have been doing all along. You specify your function template, but after the parameter list, as we see here, you're going to put your requires clause, and you can put that in this place here, and it is going to work. I realize these are many syntaxes to process for the first time, but some of these syntaxes are going to work better in some situations, and they are there just to make it flexible for you to use concepts in your C++ code. Okay, now that we have seen different ways we can set up concepts for our function templates, I think it is big time we headed over to Visual Studio Code and tried them out. Okay, here we are in our working folder. The current chapter is concepts. The current lecture is using concepts. We're going to grab our template files. We are going to put them in place. And we are going to open this thing in Visual Studio Code by dragging and dropping on top of Visual Studio Code here. We do that. This is going to open our folder. We're going to open up our main CPP file and close the sidebar here. And we're going to clean things up a little bit. And we're going to set up our function template, which is going to add two numbers. We already know how to do that. So we're going to say template type name, and it's going to have a template parameter of T. Then we're going to set up the function like we have been doing all along. We're going to say add. We're going to say TA and TB, and this is going to return the sum of A and B. Once you have the function in, we can go in the main function and set up code that would call this function. And if we try to compile this program, it is going to work now because we are not placing any constraints on this function template here. Let's try to build with GCC like we have been doing all along. You see, it is going to build. Okay, you see the build is good, build finished successfully. And if we want, we can run this application and it is going to print result A, result B. Let's take this out because we haven't done this yet. But it's not going to print result C, but if we want, we can really print it. It's going to work. So let's put that in and we're going to say result C and print result C here. And build again. Let's build now to take this into account. Build is good. We can bring up a terminal to try this out, and we can clear and run Rooster. Now you see result A is 30 because that's the sum of A and B here. Result B should be 16, which is what we have. Result C is 13, which is what we should get by adding these two double variables. Now, we wanted to constrain this function to only work if somebody passes integral types in. When we put that constraint in place, it is going to work if we add up two character variables because they are integral types. It's going to work if we add up two integer variables because they are integral types. But once we hit this guy here with double variables, we should get a compiler error because the constraint is not satisfied. Let's do that. We're going to comment the double thing first because we want to really isolate it and see the compiler error that we get. And we're going to add a constraint to our function template using concepts. Okay, if you want to use concepts in C++ 20, the first thing you need to do is to include the library that gives us access to concepts. And we're going to do that by saying include concepts. This is easy. Now that we have this in, we're going to use the first syntax we saw in the slides, and we're going to add a requires clause after the template declaration, and we're going to say std integral, and we're going to say the template parameter here. I think this is the syntax. Okay, watch what happens if we do this. Down in the code, we are calling the function with char types and integer types. So this is going to compile fine because the concept here is satisfied. This concept is going to enforce for the template parameters we call our function template with to be integral types. Let's build and see if we get to compile successfully. You see build finished good. Everything is going to work, and if we run our program, we should see result A and result B printed out. Let's run the program. We see our result here. Now we're going to comment out the others and leave in the double example, and we're going to uncomment that. And I want you to see the problem we get when we try to use our function template with double variables here. You see, Visual Studio Code is already complaining. It is saying there is something wrong. If we look at the problems tab, it's going to say no instance of function template add matches the argument list. But this is really not descriptive enough. But the problem is our concept is not satisfied by calling our function template with double types, because we clearly said that we want the function to only be called with integral types. Let's build our program. We're going to pass this through GCC, and we're going to get a compiler error that says that some concept was unsatisfied. And we see in function main use of function tadd with double with unsatisfied constraints. And this is really clear. When we see an error like this, we will go and look at the constraints that the function has, and we're going to see if we satisfied those constraints by calling like we did in the main function here. And we will know that the function doesn't support non-integral types, and we will fix this problem. This is really how concepts can help in writing safer function templates. Now that we have seen the first syntax, I think it is big time we looked at the other syntaxes. So let's do that. Let's copy the code here because we're going to be reusing this a couple of times and adapt it instead of typing this entire thing. The second syntax involves getting rid of the requires clause altogether and just using the concept instead of type name here. So we're going to say std integral, and this is going to be enough. This is going to tell the compiler to enforce this concept for this function call for all the template parameters that go in the place of t here. I hope this makes sense. Now if we go back, you see that we still have our squiggly lines here. If we try to compile, we will get the same compiler error. Okay, and you see we have the same compiler error, function add t called with unsatisfied constraints. I think if we go down, we're going to see even more stuff out of this. It's going to say required the satisfaction of std integral with t, but now we are trying to call this with double. So this is really going to lead to a compiler error. So this is the second syntax, and it is going to do the same thing. Now that we have seen this, we also have a third way we can do this, and that's through the auto mechanism. Let's set up our function using auto. So we're going to say auto add, auto A, and auto B. We have seen that we can do that in the last chapter, and we're going to return A and B, A plus B I should say. If we do this, you see that the squiggly line goes away, and we can add these things up and print the result. The return type is going to be deduced by the compiler automatically. But know that this is going to generate a function template behind the scenes. This is just a nicer syntax we have to use auto to set up functions that work for multiple types. Let's build and see how GCC handles this. The build is good because we have no constraints here. And if we run our program, it's going to work. It's going to give us 13 as the sum of 11.1 and 1.9. But we can also place constraints on this function here. And you do that by specifying your concept in front of the auto keyword here. So for example, we can say std integral and std integral for the second parameter here. Let's say that. And once we do this, if we go down, we should see our squiggly line on the call of the function here, because now the way we are calling this function is not valid. The function clearly says that it wants to be called only with arguments that satisfy this concept here. If we're trying to build again with GCC, we're going to get the same compiler error. Let's do that. And it's going to say use function with unsatisfied constraints. The same error. And if we go down, we should see that it requires the integral concept to be satisfied here. So this is the third syntax you can use if you happen to be using the auto syntax for your function templates. Let's comment this out because we still have another syntax we need to learn about. This is going to be our syntax 3, and we're going to comment this out. And the last one involves just leaving in our function template. Let's copy this because I don't want to type this again. We're going to go down and say syntax 4 and put in our function template. We're going to take this requires clause, we're going to cut it out, and we're going to put it after the function parameter list like this. And this is going to be valid C++ syntax to enforce a concept on your function template. If we go down, you see we have this wiggly line, and I should prove that this works with other integral types here. Let's just comment out the double line here and uncomment the other we had for car and int. If we try to build this program now, it is going to build fine because the constraints are satisfied. But the moment we uncomment the calls with double types, we're going to get a squiggly line, which is a good warning that we have a problem. But if we ignore the squiggly lines and just build with GCC, we're going to get the same compiler error. And it's going to say that to call our function, we need to satisfy the integral concept for the arguments that we pass here. And the double arguments we're passing in here are violating our concept, so we get our compiler error. This is really how you can use concepts in C++. I tried and came up with simple examples to show you different syntaxes you can use concepts with. And this is really it. Try to get yourself familiar with these syntaxes, and it's not going to be really hard to use concepts in your C++ programs. Okay, this is really all I had to share in terms of the syntaxes you can use with C++20 concepts. If you go to the documentation, you're going to have more information about this, but we're going to do a few more lectures to really drive these things home. For now, you can come to CPP reference here and see more concepts that you can use. We have a lot of this, and we can really use this to tune our function templates however we want. Okay, for example, you see our integral concept, you see a floating point concepts, and there are even more that are usable with classes, but we haven't learned about classes yet, and we will do that starting in the next chapter. But now I just want you to be familiar with concepts that were introduced in C++20. And here is another piece of documentation you can look at just to complement what we are talking about in this chapter, but I wouldn't recommend reading this just yet because it's just going to confuse you. There is a lot of things we still need to learn to really be able to understand this. So try to go through this chapter, and I am going to try and break this down in ways that you can understand this. The main message is that there are more concepts here you can try in your C++ code if it makes sense for the problem you are trying to solve with C++. We are going to stop here in this lecture. In the next one, we're going to show you how you can set up your own concepts in C++. Go ahead and finish up here and meet me there.